Continued. Hopefully that got in the 10-minute YouTube limit there. Okay, I was just about done with pointing out one perspective on why this works. What this does is it simultaneously solves three systems. How do you take these columns and make I? How do you take these columns and make J? How do you take these columns and make K? And it turns out that another very efficient way to say that is if you put a matrix together with these columns and you multiply this matrix times that whole matrix, you get the identity matrix. So let me demonstrate that. Let me actually put that together. It's another basic fact about how matrix multiplication works. There's a lot of cool things simply about the operation of matrix multiplication. So I suggested earlier that you check this yourself, but now maybe we're just going to do it. Well, let's assume that we've checked these are true, because they are. Okay. And let's see what happens if we make a matrix whose columns are these three vectors. Let's just go through really, really carefully. I'm going to make this really big over here because I want to show the calculations. I don't just want to show the answer. So what I claim is that when you multiply two matrices, you can just work on, if you look at the right-hand one, if you just work on the first column and the whole left-hand matrix, that's what's going to produce the left-hand column of the product matrix. So let's see. Let's do it just in the standard way, matrix times row times column, and we'll do a few of those, and I'm just going to write them out. It's going to be 0 times minus 9/2 plus 1 times minus 2 plus 2 times 3/2. And I'm just going to not do the other columns, in fact. That's what I'm going to do. I'm just going to work out the first column. What is that doing? It's taking the first row and the first column. It totally ignores these guys. You don't need that information to produce the first column. Here, I'm taking 1 times minus 9/2 plus 0 times minus 2 plus 4 times 3/2. Again, I'm using the whole row here, but only the first column here. And here, I'll put it on two lines, I guess. 4 times minus 9/2 plus, minus 3 times minus 2 plus 8 times 3/2. And if you check it, it is 1, 0, 0. But the point I want to make is that this is exactly what you'd get by multiplying this matrix by exactly this column vector. And then to get the middle column of the product, you're going to take this whole matrix times the middle column. To get the right-hand column, you're going to get the whole matrix times the right-hand column. It's a good thing to convince yourself of by really looking at it yourself if you want, but hopefully it's fairly clear how it's organized. So that means that since this is the solution to this problem here, and this middle column is the solution to this guy, and this column is the solution to this guy, when I multiply them together, I will be guaranteed to get the identity matrix. And the one reason I mention that is that, first of all, it's a way to show that this really does give you the matrix inverse, but it links matrix inverses, which is this kind of new pure algebra kind of thing, back to the geometry more. A really, really useful use for matrix inverses and this whole idea is the idea of translating back and forth between sets of building blocks. They're called bases. This is called the standard basis of R3. That's a 0, 1, 0, remember. These three vectors, A, B, and C, would be a different set of building blocks. And I'd like to be able to say, how do I translate back and forth between them? And this is really the crucial thing, because if you can't even make the old building blocks, I, J, and K, out of your new building blocks, you really don't understand your new building blocks, and you're probably not going to be able to make anything else with them. And that's what this calculation does. And we'll probably come back to that idea of translating between building blocks, at least somewhat. Certainly in a full semester linear algebra course, we'd spend a lot of time talking about that particular idea. Let me introduce to you another way of understanding this calculation as well. Actually, let me save that for a different video. This is a good place to stop this one.